All right, today we're going to follow a hidden thread that connects the code flickering on your screen all the way back to the giant power plants humming across the globe. We're going from the grid to the code to really figure out how on earth we're going to power this AI revolution responsibly. So let's just start with a number to wrap our heads around the scale here. 120 gigawatts. That's the new power that US data centers are projected to demand by 2030. And to give you a sense of just how massive that is, it's a five-fold increase from where we are today. We are building a digital universe that is incredibly hungry for real-world energy. And that really brings us to the core problem, doesn't it? The AI revolution isn't coming, it's already here. It's moving faster than anyone predicted. But it begs the question, how do we possibly feed this beast without completely breaking our energy grids and shattering our climate goals? So here's our game plan. We're going to start with the death of a long-held belief, the idea that compute is cheap. Then we'll get into the new rules of the road for power that are popping up globally. We'll look at how we're even trying to bridge this enormous energy gap before we zoom all the way down to the real cost of writing a single line of code. And we'll wrap up by seeing how this all lands squarely on developers with what's being called the green engineering mandate. Okay, first up, the end of compute is cheap. For decades, the entire tech industry has been built on this one core assumption, and that assumption just got blown to pieces. You know, it feels like just yesterday, the name of the game was scale at all costs. It was this mad scramble for more and more computing power. And honestly, nobody was really looking at the energy bill or the environmental footprint. But now, the tables have completely turned. The new mantra is responsible scale. Sure, you can grow, but you absolutely have to square that growth with your net zero promises and the very real and very painful spike in energy costs. And this has led to a really powerful new concept, carbon debt. And here's the kicker. This isn't just some feel-good environmental term. It's a hard-nosed financial reality. When a company spins up a new data center today, the emissions from all that steel and concrete, plus the power it's going to suck up for the next 10, 20 years, all of that now sits on their financial books as a long-term liability. The choices you make today will haunt your balance sheet for decades. Now, this shift isn't just happening because CEOs had a change of heart. No, it's being forced on them by governments all over the world. Which brings us to the new rules of power. And what's wild when you look at this is just how coordinated and global this is. I mean, look at the EU. They're making companies literally pay for the carbon that's baked into their hardware. And they're demanding these incredibly granular reports on energy and water use. Over in the US, the feds are creating standardized rules for how huge power hogs, like data centers, can even plug into the grid. And in Singapore, the price tag on a ton of CO2 just went through the roof. Basically, there's nowhere left to hide. And this quote from the European Commission, it says it all, really. They want a standardized system with transparency. The whole era of fuzzy math in sustainability reports and just kind of greenwashing your way through it, that's over. Now, it's all about cold, hard, verifiable data. You got to show your work. Okay, so demand is skyrocketing, and the regulators are cracking down. How in the world does the industry actually fix this? That takes us to Section 3, bridging the energy gap. And the strategy is playing out on two different timelines at once. For the short term, it's all about something called load flexibility, which is basically a fancy way of saying we need to get way smarter about using the power we already have. But for the long haul, there's just no getting around it. We have to build an unbelievable amount of new, clean, and reliable power from scratch. So let's talk about that near-term fix first. Load flexibility isn't just about turning things off and on. It's about intelligently shifting compute jobs around. And the research on this is pretty stunning. Simple things like tiering your workloads can cut peak power use by 25%. Now, if that was done everywhere, it could unlock a mind-boggling 126 gigawatts of power that's already in the grid but is currently stuck. And this shows you how serious this is. In places like Texas, this isn't a suggestion anymore. It's becoming the price of admission to even connect to the grid. And what about the long game? Well, the hyperscalers, Google, Amazon, Microsoft, they are making huge, expensive bets on what's called clean, firm power. That's the holy grail. Power that's low carbon, but is also there for you 24/7. They're looking at everything, using natural gas but with carbon capture as a kind of bridge technology. They're investing heavily in next-gen nuclear, like these new small modular reactors, and they're exploring geothermal and hydrogen. Every single one has its own challenges, for sure, but the race is on. Okay, so we've been talking really big picture, grids, regulations, power plants. But now we're going to pivot. We're going to zoom all the way from the macro level down to the micro, to the code itself. Welcome to the very real physics of software. If you've ever taken a computer science class, you've definitely run into this. Algorithmic complexity, or big O notation. It's the language we use to talk about how efficient a piece of code is. Well, get this. In our new energy-aware world, we're not just measuring that efficiency in time anymore, we're now measuring it in kilowatt hours. And this table just lays it all out. If you write a pretty efficient algorithm, something like O of n log n, that's the new gold standard. But if you write an inefficient one, like O of n squared, it doesn't just run slow. It sets off a quadratic energy explosion. It creates these intense spikes of heat right on the processor. And it's so important to get this, that mathematical messiness has a direct physical impact. That heat forces the chip to protect itself by slowing way down. We call that thermal throttling. If it gets bad enough, you get something called dark silicon, where the chip literally has to shut down entire sections of itself just to avoid melting. Think about that. Your bad code is turning off parts of the computer. And it's not just about the structure of your algorithm. It turns out the actual programming language you choose to write in makes a difference. Studies have shown that some languages are just fundamentally more energy efficient than others. You can see here Java and Go are pretty good on energy, but C#, at least in this study, used a lot more. Every single decision a developer makes now has an energy price tag. So, where does this all leave the actual person writing the code? Well, that brings us to our final section, the green engineering mandate. The actual job of being a software developer is changing, fundamentally. A senior dev isn't just someone who can crank out new features anymore. They're now expected to be a steward of global resources. They have to think about the carbon return on investment for every single thing they build. And this isn't just a vibe. It is being hard-coded directly into their tools. The modern development pipeline, what they call CICD, now has energy checks at every single step. Developers test energy use on their own laptops. The automated system then measures the actual joules that a new feature consumes. And if that code goes over its energy budget, the build fails. It's rejected automatically. It never even makes it to a server. And this really gets to the core of the new reality. Bad code used to mean it had a bug, or maybe it was just a little slow. Not anymore. Today, bad code is wasteful code. It's code that accomplishes very little while burning through a ton of power. And the new systems are designed to stop it dead in its tracks. All of this leaves us with a pretty fascinating, almost philosophical question to think about. For years and years, developers have talked about elegant code. Code that's clever or beautiful in its logic. But in this new world, this energy-starved age of AI, has the very definition of elegance shifted? Is the most elegant code now just the most efficient code? Because what we're seeing is that these three ideas, mathematical elegance, physical reality, and global responsibility, they aren't separate things anymore. They are all tangled up together, completely linked. The abstract world of software now has a very real, very heavy physical footprint. And frankly, the entire future of software depends on us getting this right.